We have people joining on here. I'll just maybe summarize where we're at for everyone, and we'll have some people joining as well at the same time. So this is the fourth webinar in our SENTRY webinar series. For everyone or those that missed out on any of them, the first one was relating to toxicity in wastewater streams with a specific look at the pulp and paper industry. Our second webinar we did with Wastewater in the UK, looking at aeration optimization. And then last week we went pretty deep in the data, and that was a 12-month look at wastewater influent conditions at one of the largest wastewater treatment plants in Illinois, having a specific look around inflow and infiltration, how that impacts the performance, not just in terms of carbon loading to the facility, but also downstream nutrient removal. Super interesting. So now this week, it's webinar number 4. I'm really excited about this one. Basically what we're looking at here is looking at microbial activity, looking at organic carbon in wastewater collection systems. And the key for me really when we were looking at this was, you know, it's not the most common application for data, for sensors, for understanding wastewater, but it's really important. And certainly being able to understand where the organic load is coming from certainly could really be helpful from a process, understanding process and process optimization standpoint. So with that in mind, one last thing in terms of housekeeping, if people have any questions, feel free to just ask the questions into onto the Q&A or the chat section there at the bottom, and we'll hold the questions to the end. But do type in your questions as we're going through. Feel free to do that so that we have those. And I think that's it. With that in mind, Jack, I'll hand it over to yourself and Amy Gamache from Western Environmental.
Awesome. Thank you, Patrick. Yep, so today we're hopefully going to talk about bioelectrode sensors for wastewater collection monitoring with a case study in Arizona. So just to introduce you to myself and Amy Gamache. Amy Gamache is she works for WEECI, Western Environmental Equipment Company. She's worked in the she has a bachelor's in mechanical engineering from Northeast University. She's worked in the wastewater and water treatment industry for 14 years as a manufacturer's representative. WEECI, while being a manufacturer's rep, also offers service, consulting, and turnkey options for many of its customers, including day-to-day maintenance support of equipment like flow meters, blowers, and SENTRY. And I'll turn it over to her when we get to the kind of specific site and installation details. Myself, I'm Jack Ambler, working for SENTRY. I'm an engineer by trade, worked with bioelectrochemical systems since about 2008 at Penn State, where I was working with Patrick on research and development for that technology. I've also done tech development, BES work at Siemens Technology of Business, and worked as a design build engineer, consultant engineer. So just quickly through the agenda, intro to SENTRY and bioelectrode monitoring, collection system and collection system monitoring basics, and then a case study around the Arizona installation. So for many of you guys who are on call 4 here, this is all background knowledge to you. I can hopefully breeze through this, but just to quickly talk about the technology again, bioelectrochemical system. It's an anode cathode pairing. We're applying a potential to create a location on the anode surface area for biology to grow and respire to. So basically, bacteria which live naturally in wastewater environments can grow in this anode. They can they oxidize organic material and donate the electrons directly to the anode. So that way we can actually measure this current as they produce it. So what we're getting here is the real-time consumption rate or real-time metabolic, organic consumption rate and real-time metabolic activity in that biofilm. Pretty standard looking sensor. Just get the electrodes wet in a wet area. Looks like a DO pH probe. Most of our installs come with a SIM card, which automatically ship data up to a web viewer, so you can kind of get that plug and play aspect of the data. Again, a little bit of review, but just kind of the 3 ways we characterize the data. The first one, toxic impact characterization, or large immediate change types of characterization. In top left here, you can see kind of very steady state for the first 10 hours of running, followed by a large chemical or organic in this case, an inhibitory compound gets in there, causes decrease in, the metabolic activity or the organic consumption rate. You're at about 50% after 12 hours, so you can get an idea of exactly when it hit the biology, when the, basically how bad it hit the biology, and then you can get an idea when if you span this out, how long it would take to return to steady state. Organic carbon quantification, we're a measurement of the real-time consumption rate of organics. So, it's a kinetic-based measurement. So as you can kind of think, increased carbon quantification or increased carbon, we get increased metabolic rate. Decreased carbon concentration, we decrease the kinetic rate. So you can see how the organic quantification works out. And then third piece is just that we get a data point every minute. This is an example trend of it, and I'll go through one, so I won't go through much of it here, but really it's just showing you the value of, if you have a data point every minute, you can do all sorts of great statistical tools, use statistical tools with it. You can do, you can fill in data sets that that your other sensors might be, taking grab samples or whatever, or taking longer. You can kind of fill that data in with all this additional data. And just, I'll be real brief on the install, but NEMA 4X control panel, typical sensor install. It's like a 2 to 3 hour install. You're just trying to get it into the system in a representative location. And we can, and like I said, you can get data going up to a dashboard right away. I would mention that the catalyst, since it's a biofilm and not some sort of optical or rare earth metal or anything like that, doesn't require any specific maintenance for the catalyst itself. The only type of maintenance we're worried about is clearing debris from the sensor that might accumulate on it. But things like we're not doing any sort of conditioning the catalyst like you would with a lot of other systems. So go through, hopefully as a collection system basics, maybe we start to get a little bit further down there too. But so kind of the traditional collection system, this is how most people would see their wastewater collection system. The goal is to effectively transport wastewater to the plant, and then we'll deal with it from there. So this can often be managed by a separate branch municipality, maybe a collection system group. Might not be communicating with the operation team very much. In the simple image on the left, you've got a business or residence leading up to one wastewater treatment plant. All seems very easy. And kind of the goals are, don't lose any on the way, due to clogging or pipe failures, and don't add too much on the way due to infiltration, inflow and infiltration. So that's kind of the traditional view of a collection system. What we kind of find is it's actually a complex and living and growing entity. It's constantly being added to, stretching the original design or changing what the original design parameters are. You're looking at a lot of different sources. You have, industrial, you might have multiple communities. You may have intentional or unintentional illegal dumpers. You're gonna have commercial in there. You're gonna obviously have stormwater impact, I&I type of impact. And all these different impacts kind of have their own unique patterns. They might be, they might be very far on the collection system and take a long time to get to your system. They might have a batch cycle. They might be a diurnal pattern. So all these are coming together and feeding into, the wastewater treatment system. And then in the more complex one, we're actually adding multiple wastewater treatment systems now, where you have, one, not necessarily all the flow going to one, but splitting the flow up amongst multiple. Also, kind of an interesting piece is some of this potential storage that's being added on. And this can be kind of as minor as, hey, we've got extra pipe capacity due to, lower flow patterns these days, or more water consumption, or less water consumption, more water conservation. So you can, that might be as simple as, moving fluid around your collection system to prevent some of this I&I peek through, or it can get as complex as a built-in storage tank. So yeah, that storage potential can be interesting and can add a lot of complexity to the system. Also, all these different partners now and potentially different treatment people, the accounting for this system has become much more important. So figuring out who is contributing the load, make sure they're paying for it, and who's actually processing the load, and make sure they're getting paid for it. So I think the accounting of the water system is getting better, and it's getting more important, as Mamie's going to talk about in the case study a little bit. Yeah, and identifying these loads, figuring out again, who's responsible, figure out who's illegally dumping, either intentionally or unintentionally, maybe even just, maybe they're not even aware they're over dumping or under dumping. Kind of a nice, interesting go forward here, and some of the Arizona plants are starting to do a bit of this, is actually kind of like an ultimate feed forward control. So, a typical wastewater plant might have upfront sensors that, might give you an hour or two's heads up before it hits your biological system, or maybe a little bit less than that. If you can get an idea of when these systems are coming to the plant well ahead of time, you have all sorts of options of, ramping up your system or diverting the flow somewhere else, or, into your retention areas, or to another plant. So you have this ability to move organic loads around and to fit the plant's needs and weaknesses. So, if one of your plants is currently in a heavy loaded system, can you ship it to the other plant? And the same for when they're underloaded. Can you move perhaps storage through the plants when they're underloaded? Just to kind of separate the two, I think both of these are very important to measure, are two very important pieces to measure in this collection system. You've got hydraulic data and you've got organic data. Hydraulic data, that tends to be hydraulic capacity for the plant. So that's plant overflow issues. Are you going to overflow the plant? Are you going to force too much liquid through these clarifiers? The clarifiers have a lot of their stuff is based on flow, just flow rate, not necessarily concentration. Are you going to push too much of your, return activated sludge or waste activated sludge out of the system by doing sludge washout? And it's kind of oftenly, driven by the I&I events. So you're kind of primarily worried around big rain, melt, or whatever types of I&I conditions. As far as organic loading, this will be considered organic loading capacity. Most of your bioreactors and perhaps some of your chemical addition systems would be designed around this. So these are the ones that you'd be worried about over stressing. And so this is the balance of food to mass. Make sure you've got enough biomass, which has enough contact time to treat the organics to treat the wastewater to the appropriate levels. This can also be important in B&R plants, balancing the carbon to nitrogen to phosphorus ratios to make sure that you can run that B&R and BioP process. So changing organics for that can be very important. And it's also kind of a little bit more important than flow for catching illegal dumpers, because again, like I said, illegal makes it sound really bad, but sometimes it's got people who aren't realizing or don't have particularly good setup at their own site to catch it. But essentially, this would be normally much lower flow, so you're not going to see some massive influence of flow. What you might see is a large increase in organics. And these tends to be very high concentrated wastewater. So an example of this would just be, like a medium-sized craft brewery. I hate to pick on the brewery guys, as I'm relying on them just as much as anyone else during the COVID period here. But they are a very common and easy one to work with. So kind of a small plant, 1,000 gallons per day of beer production, or a medium-sized plant with only minor treatment. They'll probably be paying around 40 cents per pound of BOD. So pound of BOD being, concentration times flow. And that might be as much as $125,000 per year of surcharge fees or something like that. So if you're spending somewhere around, $10,000 per year to monitor, which would be similar to, a SENTRY style equipment, all you really need to do is make sure you're accounting them to at least an 8% deviation from the pay. So essentially, if they're underreporting by 8%, you're immediately paying for itself. And, often with any of these industrial partners, the way to make it work is you need to bring them to the table, and maybe some on-site treatment or something like that would work out better for them. But you normally can't do that without solid data to back it up. So some of our clients have used that aspect as well to kind of track an industrial load, bring them to the table, let them know that something's happening, and then they can hopefully implement better discharge cycles. And for this, grab samples simply aren't going to work. These batch processes, all these industrial and a lot of the commercial ones, are not typical like residential that you'd be getting high, like relatively small change. You might see 10 to 10,000 times increase in the concentration depending on what they're doing during that time. And just to talk a little bit about some of the extremes on the storage options. So like I said, people can be using their own collection system to do this by just intelligently moving flows around. That's kind of good for, hey, let me deal with this small flow rate, but for something like Cleveland, Ohio, this is the Easterly Tunnel dewatering station. In 2016, it was built. It was an $80 million project. But basically what they were dealing with was their plant and their collection system were not able to handle about 4 billion gallons per year, which were flowing directly into Lake Erie. So they built this kind of cavern style pump station. It's about a 160 million gallon hydraulic retention time, or sorry, 160 million gallon volume for to hold in a 3-mile long single pass concrete line storage channel. So this is kind of an interesting, this gives them a ton of flexibility to hold flows. And this is similar to the work you were talking about last week with Illinois, with being able to hold this. And that's kind of the hydraulic-ish part of it. And as we were showing, and as we've seen, there's also a carbon aspect of that, and a sediment aspect of that, and other compounds coming in as you move a large amount of wastewater into this type of holding tank, or stormwater into this holding tank. There's biological process taking place, there's sediment transport happening. So understanding what that load as it comes to your plant can be additionally helpful. And you know, like we were talking last week, it can have an interesting effect on your carbon and nitrous to phosphorus ratio, and and the bioavailability of the carbon. So just to sum up what we think, some good sampling requirements would be to actually take, effective action. On location analysis with high resolution, we think real time. We should really be moving entirely as an industry to as much real time data as possible. It just gives people the ability to actually respond to it, and that kind of resolution also increases, can really tell you what's going on. Grabbing composite samples are good, but they only confirm after the fact. There's a lot of testing costs associated with, which Amy will talk a little bit about with the Arizona install, but also it's a very lag time for actually getting the data in your hand. You need low maintenance equipment. As many assets are difficult to access or remote. You might have to shut down a road to get into these. Also, collection system wastewater is historically even nastier than what's going through your wastewater plant, or even more difficult to manage. So low maintenance is important. And then we kind of have a remote data collections for usage as the data comes in. So you have to collect it quickly, and you have to be able to transport it to operators' hands as quickly as possible so they can take action on it. And with that, Amy, I'll throw it over to you here with a bit of you can walk us through some of the installation and some of the Arizona case study work that we did with you.
Okay, thanks, Jack. Hi, good morning, everyone. So here in Arizona, we have an instance where there's multiple municipalities that actually send all of their wastewater system to one large municipality here, the city of Phoenix. And the cost, we have to figure out how to cost. There's 5 municipalities that send their wastewater and don't treat it. They send it to Phoenix to be treated. And the cost to divvy up to treat all of this is a little bit less than $50 million a year in revenue. And so they currently do that with flow monitoring and sampling. So there's a number of stations throughout the collection system amongst all the municipalities where they continuously monitor flow. And then once a week for every month, they do 24-hour a day, 7 days a week composite sampling so that they can gather that COD and TSS data to be able to calculate loading. So those samples are great, but they're just small pinpoints of what's going on that particular week for loading purposes. And the cost to do that sampling for each station runs about $100,000 a year per site. And not only that, but then you have all the sampling equipment to take into consideration that needs to be, that they replace approximately every 7 years. Plus they have all the staffing required to do this on a continuous monthly basis. Go ahead, Jack. So we have a site, it is considered a overall trial site where they actually try a number of different pieces of equipment. And the deal with these guys is it has to be in for at least 3 months, and they have to get good data from it for 3 months before they would actually even consider it. So at this particular site, we do have an optical probe that has been in there for approximately 5 to 6 years now. And This site is completely domestic, or it's all domestic wastewater that goes through this site. It's easily accessible. The one caveat is it's in a neighborhood of over $1 million homes. So it's a little bit sensitive from a political standpoint, but it's very easily accessible. And that's why we trial all of our equipment there, because it doesn't cost us anything in traffic control to access or do any maintenance or updates or having to shift the equipment around. So we decided we wanted to put the SENTRY in at the same location as the optical sensor, because we wanted to go head to head with the optical sensor to see how it did. So this is a flume. It's a partial flume, 27-inch partial flume. This site has a large diurnal pattern. From the height to the least amount of flow, we can have 8 or 9 inches in difference of water height. So we have to mount this sensor close to the bottom of the channel. And you can see that we put a cage around the sensor just to try to help, because we do tend to have ragging issues at this site. And you can see in the installation that it's actually against the sidewall of the flume, or the wing wall of the flume, so that we can ensure that the rags go by. You can see the velocity picks up in the middle as it is focused through the throat of the partial flume. So we used the optical sensor, and we use a Teledyne ISCO laser flow meter upstream from this. And this is how they're calculating the loadings at this particular location. And they still do sample here because it's an ongoing trial, so that we can compare the sample data to both sets of sensors. Jack? This is a picture of the laser flow meter that is upstream. It's they've standardized on this particular flow meter because it's a billing application flow meter. And again, we can also, once this is installed, you can remove it without having to do a confined space entry. So the key to our sites is trying to keep them as minimally requiring maintenance as possible. So right at the beginning of COVID-19, we ran into a little bit of an issue. Again, I mentioned that this location is completely domestic wastewater. And so with the stay-at-home orders, we saw a difference in the sensor data. So we went out to the site and we saw that there was quite a bit of paper buildup and residual fibers all over the outside of that cage. And this picture is actually after we kind of, what I call, swished it in the water. So we dismounted the probe from the side of the wing wall, and we literally just swished it in the water back and forth to clean the majority of the debris. We pulled it out because we did have some fibers on the actual sensor itself, and we very gently cleaned that with a chem wipe. The maintenance, in 6 months, we've only had to do this once. And it literally took a half hour from the time that we started to the time that it was completely finished. It takes longer to dismount the unit from the sidewall than it does to clean it.
Excellent. Well, great. Thank you very much, Amy.
You're welcome.
And yeah, just to kind of show some of the data that we collected at the site, try to get you guys some real-time results here. So this is some of the data compared to some of the light-based sensor results. In this location, so this is blue is the blue signal is the MET data, or the SENTRY data, microbial electron transfer, or organic consumption rate, and the yellow data would be the installed COD measurement. So the CODs, this is a light-based sensor. It'd have to be a whole other talk to discuss, how those work, but essentially shining a UV light into and measuring the reflection back. So yeah, you can kind of see the response. This is about a week's worth of data. You can see kind of certainly the immediate pickup with the data happens pretty coinciding with the SENTRY data. You can certainly see the 24-hour cycles as we're seeing, from for each day. You can see a little bit of the 12-hour cycle, which is kind of the second pattern in the COD, in the optical data, and you can see it a little bit more pronounced in our MET data. It's kind of an interesting, we do tend to see about a 12 and a 24-hour pattern at most wastewater facilities, at most locations, as you have a lot of the, wake up, going to work, go somewhere else to, for the day, big shower when you get home or when you leave. All that type of stuff tends to be pretty common to have a 12 and a 24-hour cycle. It's a little bit interesting to see how, spikes up the same. The COD data drags off a little bit slower, where ours is a little bit more pronounced. They also have an estimation. So I think they take the one signal and then they do an estimation, kind of a universal application to estimate soluble COD. And just to kind of reconfirm what we're measuring here, we're measuring what's relevant to the biology. So what is actively being consumed by biomass. So we're, the number of electrons essentially being consumed by biomass, as opposed to, a COD or a BOD style metric. But here you can see kind of the comparison with the CODF, fractionated or soluble COD, sorry. Again, in this one, you can see rapid uptake, a little bit more of a flat line at the top for the COD, where we just clearly have the diurnal trend, and then kind of a rapid drop off before these low values. So you can kind of see the nice overlay with it. You can see the nice 12 and 24-hour cycles at the location. And with kind of this type of data, when you're getting this much data metrics, ours is every minute. Theirs, I think, is about every 15 minutes here. You can kind of see, trends. And for example, we also saw kind of a 21-day trend besides the 12, 24, and weekly pattern. And just to show a little bit of the weekly pattern, and we can do this at all sorts of locations. You've probably seen it in the other talks as well. There's a blue and a yellow here. There's two time periods overlaid, but don't worry about them too much. One's just at the beginning of the trial. One is a 3-month data set. I believe the blue is the beginning of the trial, and then the yellow is kind of a more 3-month, a little bit longer look. But you can see they overlap quite nicely. And you can also kind of see, all right, what is the pattern at this location? You can see, this is Sunday to Saturday, so this is a weekly. You can see, the Sundays and the Saturdays for this location is historically higher. You can see the loading's a bit lower during the midweeks, Tuesday through Thursday, with Monday, Friday kind of being average. Again, green being the average loading. And you can also see exactly when these loads are happening at this location. So you can see, kind of their first peak is this 10 to 12 p.m. They have a small valley at 6 p.m. and then a second peak around midnight. 68, so yeah, and this kind of lowest time period is 6 to 8 a.m. as their lowest concentration. So it's a very interesting look into it. It's very repeatable during this time period. And this, you can see how you can kind of combine, obviously at the plant at the very end, once they receive this data as uniformly as possible, or receive this flow as uniformly as possible. So understanding kind of each location's pattern can be valuable for the downstream plant. This is just a bit of the event detection aspect. So our sensor, like I said, is a biological, giving you a biological signal. So it can do event detection as well. So this was just an interesting time in the October 31st and November 4th time period. So these are 2 days overlaid on, this is kind of our standard graph from the dashboard. And the time I've highlighted shows you kind of an abnormal time period. You can see, so most of them are this, 12 and 24-hour spikes. These 2 days specifically, about 4 days apart, had a great inhibition on the biology during this time. And interesting from this is when you overlay them, they happened almost exactly at 10 a.m. and finish almost exactly at midnight. So it was kind of and 4 days apart. And as soon as you start seeing trends like that, where it's, at a certain time, as opposed to, that tends to be something, that would be like a human kind of interaction with it. It wouldn't just be, natural chance for it or something in nature typically to do something like that. So just kind of an additional level of detail that we would see on the, the SENTRY equipment, which would not be, in this case, wasn't reflected in the light-based metric, as this is a, biological event. Just to kind of reconfirm, some of the stuff we've been seeing since COVID is, I think you guys are all dealing with the same issues around the globe here. And we showed a little of this with the Wessex data 2 weeks ago as well. And we've seen this at a lot of our plants. So you can see kind of both, a typical week back in November or October, you're seeing great variability. You're seeing these very large drops of, you might have 150 MET variation. You can see there's clear weekly trends higher Saturday and Sunday. Since now, this is 3 weeks of data overlaid on top of each other. And this is after Amy was able to clean the sensor. And you're able to see we're changing almost nothing. We've got a very small change, and every day is almost the same, right? You don't see Saturday being much higher or the Sunday being much higher anymore. You can see very high levels of consistency, which we've seen in a lot of plants, which is very interesting to us and I think very relevant for operation. And as you guys are all aware, every day feels like the same, and I guess our wastewater is kind of reflecting that as well. So just to sum up, some of the high points from the collection system monitoring. Collection systems become more complex, and they're more of a moving piece of the entire of your entire plant, of your entire infrastructure. They can be utilized to effectively to help your downstream infrastructure. There's potential for plant optimization. There's ability to take response action either to storage or to divergence with appropriate monitoring. But you really kind of need flow and monitoring to get flow and organics to get the full picture. You need, how much is coming hydraulically, and do I have any bad actors, from organics or inhibitory kind of compounds that might screw up the plant or might highlight some of this illegal or unintentional dumping. Sampling needs to be real time and low maintenance. These are difficult locations to get in, and you really need, in order. The value of getting the data ahead of time is only valuable if you're getting it ahead of time and not after the fact. Municipalities such as Arizona and others, they have critical dollar requirements attached for monitoring and appropriate accounting of this. It's becoming very efficient and worth it to put these types of systems into locations to make sure you're getting the appropriate accounting balance. And SENTRY is an option for real-time organic consumption rate. Showed some interesting responses on the site, good matching with some of the traditional methods. Diurnal nature reacts to toxic compounds, so some interesting stuff around COVID, and with a low maintenance requirement. So yeah, I think it was 6 months into the project that it was our first maintenance requirements, and so that would be now 1 cleaning in 9 months. So with that, I'd pass it back to Patrick and answer any of your guys' questions you might have.
Oh, thanks, Jack. That was remarkable. Thanks, Amy. Thank you very much, both of you guys, for that. We do have a bunch of questions there, so I can get stuck into them as well. Before I'm going to be selfish, can I ask a question first?
Please.
The weekly loading, and maybe this is to Amy as much as anything. So in terms of that weekly loading, Amy, normally at that location, it's showing higher on the weekends and lower during the week. Intuitively, it points, at least in my mind, to think that, is this a community that people are often commuting so that they're just not at home during the week, and then on the weekends everyone's at home? Or why? Can you maybe talk or just explain why you think that difference exists?
Sure. Yeah, this is a higher end community that, yes, most people work away from the home. And so that is why we see that higher loading on the weekends. We also see it actually changes from summer to winter as well, because we have higher loadings. It changes throughout the winter because we have a higher population gap in that area, because we have what we call snowbirds that come to visit and live there on a monthly basis. The reason why we picked this site is because of this diurnal pattern, and it has been repeatable. We have 5 years worth of data from the optical sensor that shows this data. And like Jack showed, that the SENTRY showed an event that the optical sensor didn't. We have so much data that we can show that after a monsoon, we can show that the loadings go down for a day or two, showing the INI in the collection system, and then it recovers on its own as that INI washes out. So yeah, this is a pretty representative of just strictly a neighborhood. It's a neighborhood setting where all these flows come from. So it's very predictable, and when it is out of range, there is definitely something that has to be investigated and looked into.
Fantastic, fantastic. Thanks, Amy. Okay, so I'll go through some of the questions here. The first one, I'm actually going to put it to you, Amy, and I'm not going to, so the question is, what is the optical sensor that's being used? Maybe you don't have to mention, if you don't want to, the brand or the company, but just high level, what type of sensor is it, maybe, if that was possible?
Sure, it's a UV and a UV visible sensor. So it measures from 256 to 750 nanometers. So it's measuring the whole visible and invisible range. And then from that, they actually can calculate the organic as well as inorganic loading. We divulge to both companies that we represent both companies. We have the optical sensors around the cities. We have multiple installations of the optical sensors. Their cost is significantly higher, and in most cases, the maintenance is significantly higher as well. So the reason why we have both sensors is our thought is throughout the collection system, you can maybe put those more expensive sensors at critical junction points for alarming purposes. And then you can use the SENTRY as well. And we can follow a hit or an organic loading or something abnormal in the system to allow the wastewater treatment plants plenty of notification time to either ramp up the blowers or divert or do whatever is necessary.
Fantastic. Fantastic. Okay, the next one. So Jack, I'll put it to you. How is the sensor calibrated? Do you want to speak to calibration?
Yeah, so there is no, calibration on the, on the actual electrode surface area. So you're not doing any sort of maintenance or changing of that. We are a kinetic measurement. So the only, I think typically what happens is part of our service is that we do a 3-month trial with somebody. During that time, they may continue to take their kind of standard, measuring, measurements and standard parameters, and we can, then kind of look at giving you some idea of, this is the estimation of compared to your standard parameters. So there's no on-site putting chemicals past it at certain concentrations and all this. There's not a lot of maintenance and issues with the sensor itself, but during that 3-month trial period, we can certainly match up some of our signal with some of your signals to get a good idea of what we're tracking with there.
Fantastic. Jack, I'm going to put one more to you that's, I think you'll be good for this one. The sensor, so can the sensor measure the ammonia and nitrogen along with the organic load like BOD, COD? Do you want to maybe just comment on, just reminding people what the signal is, but maybe how it can be correlated to those components, or?
Yeah, so right, we are just an organic consumption rate, so we do primarily react to carbon conditions in the wastewater. At least at these type of locations tends to be limiting. I think if you look at some of those locations where ammonia or phosphorus is limiting, or any of the building blocks for life are limiting, we start to be able to be somewhat predictive of issues associated with that. But yes, we would carbon is a critical part of those processes, and if, for example, your carbon load is coming at the same time as your ammonia load, then it's it's somewhat relatable. But I would suggest that if you're very concerned with the ammonia load, that an ammonia sensor or something like that might be valuable to add on as well.
Okay, so otherwise, I think what I'll do is I have a few questions that I'm going to follow up with Abid Khan relating to costing. In terms of costing, actually, I'll just speak to that. So traditionally with the SENTRY platform, with most installations, we provide a control panel and 2 sensors. We provide equipment primarily around problem statements, and that equipment and service typically costs around $10,000 per annum for that service. We can also offer capital sale of equipment, and we can quote on those individually, depending on where the client is based. Okay, so I think that's it. Thank you very much, Amy. Thank you very much, Jack. And thanks everyone for joining us over the last month. I think we've really, shown some great insight with the SENTRY platform across the 4 different problem statements. So if anyone has any other follow-up questions, feel free to reach out to Jack. You can see Jack's information there, Amy's information there. If anyone has any other questions, feel free to reach out. And yeah, thanks everyone for joining. Thank you.
Thank you.